Alrighty, welcome back. The next talk is going to be given by Chris Burr, and he's going to be talking about Nix for software development in high energy physics. And I'm sure that there is a joke about Nix not being rocket science and physics in there somewhere, but I'm just going to skip it and give the mic to Chris. Please give him a little round of applause.
Okay, yeah, thank you very much. Okay, so I'm going to start by just giving you a little bit of background of who I am. So I'm an experimental particle physics PhD student, so at the University of Manchester. So none of my actual stuff that I'm supposed to be doing is to do with computing and this kind of stuff. This is just a side project. I'm supposed to be working on physics, but I get frustrated with some of the computing stuff we have, so I have lots of side projects trying to make it better. Okay, so to give you a little background, so the experiment facility that I work at is on the Swiss-French border near Geneva, and is called CERN, which is a laboratory that's been around since about the mid-1960s, I think. And the main attraction there is the Large Hadron Collider, or LHC. So this is the largest particle accelerator in the world, which is a 27-kilometer radius. So here you can see a nice aerial picture, and the yellow line is where the tunnel runs about 100 meters underground. So this is a really just huge, expensive machine. And this is used for fundamental physics research. And here, the actual machine itself isn't the bit that's used for physics. That's just used so that, that you can have experiments based around the ring that then can measure things and study how the universe works. So there's four main experiments, ALICE, ATLAS, CMS, and LHCb. And then there's three smaller ones around the ring. So the large experiments have at least 1,000 people working on them. I think the biggest one's about 3,500 people. And the smaller ones can be anywhere from just a handful of people. And then the LHC isn't the only thing at CERN. There's also a lot of other experiments, more than I can fit on a slide, but it's at least 15 or 20 when I tried to count the ones I could find. And the thing that pretty much all of these have in common is that they have a lot of computing. So the bigger experiments have huge amounts of computing requirements to do, but even the smaller ones have less people to work on maintaining their computing stuff, but sometimes still are using huge clusters and having to do lots of computation. So I'm a member of LHCb, so that's, depending on how you define it, the smallest one of the four big LHC experiments. Though the smallest means that there's about 800 physicists like me working on there, with about 400 technicians working with it, so still quite a lot of people. The experiment itself is located about 70 meters underground. Here's a picture of it with some people that were in the collaboration at the time superimposed, because you're not allowed to have that many people underground at the time. And the experiment was designed to, I was very disappointed when I found out that people were superimposed. So the experiment was designed to study the differences between matter and antimatter using the decays of beauty hadrons, but this has since been expanded out to cover a wide range of fundamental physics research. But I'm not here to talk about that today. But this is just to say that this talk is somewhat biased and just talking about what my experience with LHCb is, but the wider community has similar things, and we're somewhat working together on trying to improve this stuff. So for what computing looks like for us, so the Large Hadron Collider, particles spin around it, and typically protons smash together within the detector, and we use the detector kind of like a camera to take images of what happened. However, because we have to take a lot of collisions to be able to find anything interesting, so we have about 30 million of these images being taken per second of what happened. If you then look at the amount of data that this means coming out of the detector, that we have some tens of terabits, maybe 20 or 30 terabits of data coming out of the detector, far more than you could possibly hope to store and do anything with for long term. So we have to come up with a system of reducing this down. So for this, we have a network of a few thousand machines that are located near to the detector, going to be located near the surface, probably at the surface. And those have the job of reducing this few terabits per second down to a few gigabytes per second. And the reason this can work is because most collisions we have don't contain anything that's necessarily that interesting that we don't understand. So we need to, so all these computers are working to select out the this particular snapshot that we took of what happened looks interesting. These 100 don't look interesting. So it does a really good job of filtering down, but the process of separating this out really isn't trivial, and a lot of work goes into trying to optimize the software so that we actually can process the data this quickly in an amount of servers that we can actually afford. But 10 gigabytes per second coming out of the detector might be just about enough that you can actually store it for a long time. but it's still a huge amount of data to actually process. So probably a few tens of petabytes per data that sits on disk, and few, maybe 100 petabytes per data of year that sits on tape. So to actually process this, I can't hope to do this on my laptop. So instead, we have what's called the Worldwide LHC Computing Grid. So this is a network of about 170 computing centers, which currently has about 1 million CPU cores as part of it, and about an exabyte of storage, though this is rapidly growing as the experiments get bigger and we take more and more data. And we submit kind of batch jobs to this system to like process this for me, and this is kind of shared by all the experiments with like pledges given to each experiment. But it's a shared resource that like no one experiment can demand what is installed on all these nodes. And then kind of the last step out of this, because still even after you've processed it on the what we call the grid, we still have a few gigabytes or terabytes worth of data which then get processed on like a wide range of whatever resources we can find. So it can be like small VMs that we SSH into, or like really heavy duty workstations, or laptops, desktops, university batch systems. It's really just a mess of whatever computing resources we can find, we'll make use of. And then this final stage can last easily a year or a few years of people like really studying, trying to understand what's in that last little selection of data that they're looking at. So how do we manage packaging software at the moment? So because we can't control what software is stored everywhere, and because we can potentially have like, I think typically LHCb has about 100,000 jobs running at some point in the world with various bits of software on them. We can't just like be installing them every time, because we'll be spending a huge amount of time. We need a huge amount of infrastructure for like requesting the software to be installed. So we have a read-only content addressable file system that was developed at CERN called CVMFS. So the way this works is that you have some central node called the Stratum 0, which is the only node in which like writes can actually be made to this file system. And then once you've made some write and you kind of make a commit at this point in time, it then gets distributed out to the public mirrors, which there's typically about one per country wherever there's a significant amount of work going on. And then the way that these servers communicate with each other is just using HTTP, so that the Stratum 1s have squid proxies on them that then just proxy the files out, so that whenever you request a file, you can have kind of a proxy hierarchy, in that if I have 1,000 machines in my computing center, I'll have my own local proxy, so I don't have to go out and request it from Switzerland every single time that any file gets requested. And this works really well for distributing software around. For the actual operating systems that this software is running on, pretty much everything is using some variant of Red Hat Enterprise Linux. So the most common variant is Scientific Linux 6, but this is slowly moving to CentOS 7, and in the next few years it'll probably finally actually move to being the major one. And the way that we define the builds is that we have an architecture, so this is almost always 64-bit x86, but we're also interested in ARM if that's a way that we can get more computing power for our money. And people have also like looked at using PowerPC and more esoteric things. But basically everything we run at this point is x86. We then compile it for each operating system we support. So this is normally Scientific Linux 6, which is a RHEL 6 derivative, and CentOS 7. Some of our older software was built for Scientific Linux 5, as that was the dominant one at the time. We then specify a compiler, and we then have a last bit that we can like specify the build type, as we call it, for if we like put debugging symbols in or optimize the builds. And the way that we rely on backwards compatibility, because we keep running the software for quite a long time, is just hoping that the ABIs stay stable, and that Red Hat Enterprise Linux 6 can generally run binaries that were compiled against Red Hat Enterprise Linux 5's ABIs to varying degrees of success. The way that we then build our software on this is that there's a package manager kind of that was built by some people at CERN called LCG CMake. So this is built around CMake's external project module, and kind of builds for like some set of strings that we have like this, all the dependencies that we need for some package with some base set of system dependencies that we expect there. The way that these expressions end up looking, so like the Nix derivation equivalent, is that there is some function called LCG package add, where you define similar things with like the package name, where to download the source for the package from, and how to configure it, and all the kind of usual stuff you'd expect. And then you can specify multiple versions by using LCG external package, and then you just specify the package name and whichever package version and where you want it to be installed. So you can have multiple versions side by side. The way that the system for then storing these is that we have some install prefix like the Nix store, and then inside there you have a name for each package, a folder for each package that you have, and then inside there you have a folder which is the version of the package, and then SHA1 hash, and just the first 5 digits of it of the names of the dependencies and their versions. And their hashes that we used of their dependencies. This is how we can have multiple builds, like the way that Nix does this inside the store directory. But then on top of that, we then have the different platforms built for, and this can get quite out of hand with having a lot of different variants. So here was just one that I picked, and this isn't the worst one. This is just the first one I decided to pick, but some of them can have tens of configurations. So what are some of the issues that we have with the current solution? So probably the biggest one that can be, so looking back kind of to the past, in that before there was the Large Hadron Collider, there was the Large Electron Positron Collider that was in the same tunnel, roughly the same size, and started running in 1989 and continued till 2000. But when it finished running in 2000, the use of its data didn't just suddenly stop. It continued to be analyzed for more than a decade after, and so in 2010 there were still some people that were doing research using data that was collected in 1990 and 1995 and having to use software that's 15 or 20 years old and try and still get it to work. And this is just getting worse. The Large Hadron Collider is going to be running till 2035, so we can have at least 20 years of data taking, and who knows how much longer after that we'll still be processing data. And of course, this is longer than any operating system lasts. So right now, at the moment, there are probably hundreds of jobs running that are using software that was built in 2011 for Scientific Linux 5. And this is just getting worse as we go further and further into the future. So having reproducible builds is a really nice thing to be able to have, especially as if there's any bugs in any of the math libraries or anything that we use, we don't want to pick up a newer version without realizing, because we want to know which bugs in the maths libraries we originally used to process the data, because if not, we're never going to realize that we had those bugs there, and we want to realize them and take them into account. As I've said before, most of our current resources are Scientific Linux 6 with CentOS 7 slowly taking over. But then we kind of have contradictory requirements in that experiments are expensive and we want to get as much as we can out of them, and we have a lot of data we want to process, so we want to be able to use new compilers and new vectorization instructions and make use of multi-threading that gets easier with newer C++ standards. So we kind of want to have these bleeding edge new features, like people are working against GCC 8 at the moment within a few weeks of it coming out, while also using GCC 48 or older stacks that are currently running at the moment. So to try and bring the community together instead of everyone having disjoint solutions for this, there's an organization called the HEP Software Foundation that are trying to bring experiments together in a wide range of issues, one of which is a packaging working group. So at the moment they're trying to just look at different package managers and figure out which one is going to be their recommendation for the high energy physics community to use. And the ones that have been spoken about most recently, so there's two that are, have been developed within high energy physics. So AliBuild and LCG CMake. There's SPAC, which is one that's used in high performance computing centers and supercomputers and things, and then there's Nix and Portage, which have been looked at by various people, Nix and being me, and hence why I'm here. So what is my setup with Nix at the moment? So one of the things is that using /Nix as the store directory just isn't an option for us, because the way that we distribute software around is using CVMFS. We don't have the ability to get root access on the machines with most of the resources we have. So we already have this system in place for distributing software through this read-only file system, so it basically has to be used. And typically there is the sft.cern.ch repository that contains a lot of software, but then larger experiments tend to manage their own software installation, so they know exactly what's there, and if they need to patch things dynamically, they can do quite quickly if necessary. So for testing with Nix, I moved the store directory to be in a kind of mock CVMFS directory, so that it was as if I was trying to install the software on the Stratum 0 to this folder, but just to see how well that worked. And then as part of doing this, I ended up forking Nix packages because I found that I was needing to pull in some patches, and as well as change some various recipes and some of the recipes to build in with options that we'd need to use. And then also, as part of this, I ended up throwing in the experiment-specific software that's never going to go into the upstream repository because nobody outside of my experiment is going to be interested in using it. While preparing this talk, I became aware of the Nix package pinning and the ability to apply patches over the top of Nix packages, which looks much easier to maintain than my fork, but I haven't found time to use it because I only found it 2 days ago. So the issue with all of this, though, is because I've changed the store directory, everything takes a very long time. So you go to bed, you wake up, and either find that it's still compiling, or that it failed because it failed to download some file that it needed that's moved to the location that that package keeps their source, or a hash checks failed or something. So I ended up setting up an instance of Hydra, which, after putting this off for quite a while, thinking it'd be a lot of work, turned out to be really easy, and within an hour I had Hydra running and was working beautifully. So everyone who's done something to do with making Hydra easy to use, you've done a great job. Right now this is running inside a Docker container that then talks to an external database and has been stably running in this configuration now for several months, so I'm very happy with how it's going. Ultimately, there's a few changes that I'd like to make to it if this started to make it into production, but it's worked really well for me. So the structure of the fork that I've set up, I based it on Nix packages unstable because I found this was easier to find all the source and had fewer things where the source directories had changed. But in future, I could imagine that maybe we'd take off the actual releases, and then maybe we just apply patches and then just pick up a new release every 6 months for keeping our stacks being updated. So then I applied some set of patches over the top to change the store directory and pull in some things that I needed to actually get Nix packages to build. And then I applied an overlay over the top of this that applies any stuff that I would expect not to be upstreamed into Nix packages if this goes anywhere. And then I applied a second overlay over the top of this again, which gives what we're used to with having the entire software stack built with different compilers or with different options. So the idea is that we'd have some base release that we have within the experiment, and then we can say that we've built this with everything with using GCC 6, everything using GCC 7, or something that this might be quite useful is that to have a build that uses newer AVX 512 instructions or something, but then have one that doesn't use these newer instructions, because some of our software has this as separate builds and can't decide at runtime, and we'd want to still be able to use the resources we have that don't have these instructions available. So this is a quite useful thing to have. So for what these overlays look like, so here was my GCC 7 one, simplified down a bit. So just override GCC and to be either GCC 7 or GCC 6 everywhere, and then make some other changes that I found myself wanting to make, which was nice and straightforward. And then changing everything back to use GCC 6, I found there was just one thing that actually needed GCC 7, which was the AWS SDK, so I just manually overrode that. So it looks like this might actually be feasible for what we want to do, and maybe we'd expand these out to add some more changes as this develops. For actually running our software, we're used to using a command that's just a Python script that becomes available wherever our software environment is. That it's called lbrun. So this is kind of like Nix shell in that you run it and you then specify, in our case, a platform, a package, and a version. We have maybe 15-ish package environments that we can run with this, each one of which has anywhere from maybe 20 to 100 and something versions. And this just sets up environment variables to give you a shell that you can then work with, and then you close that shell and open up a different environment to switch between them. So I did this using build-env. So I modified Nix packages so that it gave me, I could apply the overlay path for the GCC version, then specified some list of packages, and then made this into a function which I could then specify extra packages to install on top of this. And then I put this into Hydra so that it built a new channel that just contained this built in several configurations, so it wasn't necessary to just repeat the same list of packages and have duplication, and take advantages of Nix's abilities to override itself. I'm sure this can be done better, and if you've got any suggestions, I'd love to know how, because I'm still kind of battling with understanding Nix for the language itself. So what's some of the things that I've not figured out how to do? So probably the biggest one is that all of the physicists will find that they need to develop the software at some level. Sometimes this will just be that they need to have like one development thing that they do for something quickly, which never gets committed or made into a release. They just want to like patch 2 lines in a repository somewhere to give them the configuration that we can't do at runtime because nobody ever thought of doing it. So one option to do is kind of have a completely separate tool. So at the moment we have some scripts that like work around the CMake build system that we have and like pull in the multiple dependencies, and you like just can say I want to modify this package, and it will let you run a like higher environment on top and merge these things together quite intelligently. Because all this information's inside Nix, it feels like it should be possible to like ask Nix, give me a directory here that instead of it being like built in slide/tmp, it gives you the build environment for a package in a directory you choose, and then it also can give you build environments for other dependencies along the way, and when you build it, it will link these directories against each other. I don't know how impossible this is to do, or maybe if something already exists, but it would be a very useful thing to have and quite attractive to just have one system for doing this. The idea of having Nix as a like, replacement for Make also sounds quite interesting, but that's a little way away. Another thing that I had an issue with that's a bit of a pet peeve of mine with other systems as well, because we also use Python path for LCD CMake, is that I want to encourage people to use Python 3, and as part of this, giving them Python 2 and Python 3 in the same environment is a useful thing to do. And also sometimes there's some software that only supports Python 2 and only supports Python 3, and we kind of want to mix them together to some extent. And using Python path like Nix Shell does means that you can't then import any Python libraries, because if any of them aren't compatible with both for all of their builds, then it doesn't work. So the solution I came up here was just to use site customize inside the Python build so that it uses a different environment variable to actually add a Python version specific path to each Python installation. When each Python installation loads, maybe there's another solution that people have used for this. Please let me know afterwards if you have. Another thing that we're used to having in all the systems we currently have is relocatability, so that like potentially we'll have lots of experiments that want to install this to different CMFS areas. I know this kind of goes against the purity that Nix has, so but trying it out, I thought that maybe like the way that replace dependency effectively just applies sed to the binaries to just assume that the store path is the same length, and then you can just change the store path in place because it's a huge random string that you don't expect to appear anywhere else. So I did this on quite a complicated installation and found that everything still works. So it does seem like something that could be done at installation time. But I don't know I guess there's been discussions about this before, as I found lots of mailing lists and things. And then a few other things that I'd like to find a nicer way of doing is that like a lot of our libraries need the C++ standard to be set so that everything is built with C++ 17 or C++ 14, and we mix these with different versions of software as things get upgraded to support newer standards. Also want to set other compiler options. The only way that I've thought of to do this is to just add a property attribute to the compiler itself, so then each one will like query and add its own CMake flags for the C++ standard or whatever. But maybe again this is something I just haven't found the solution. And similarly for debugging symbols, feels like this one is supported, but I never managed to get any of the various explanations of getting debugging symbols to actually work. So maybe I'll figure that out on Saturday. And then one last note before I finish. So been mentioned a few times, and I expect that a lot of these problems will be fixed with containers, though still being able to install software in a more reproducible way is still useful even with containers. And this is probably going to be the same inside HEP. I think Singularity looks the most likely inside high energy physics because of the whole Docker daemon security issues with it being a root escalation thing, whereas Singularity is designed for unprivileged users and is slowly starting to find its way into other grid sites that we have. This could also remove the need to relocate the store, which would be quite nice eventually, but this is all a long way away for now, so we'd need to find a solution that works without using containers for now. But even when we do move to containers, there was the post recently about multi-layered Docker images that mounted its way into Nic packages, and this looks like a really nice way of avoiding the problems of us previously thinking about having fat containers, and suddenly you've got huge binary blobs in effect that aren't cached, and you can get around this by taking advantage of Nix. So if you've not heard of them, look at the link, it's quite nice. So yeah, in conclusion, I think Nix is awesome, and it really works nicely for, with its purity and reproducibility for research that can last a long time. Still a few things I need to figure out, and hopefully I'll figure them out over the next few days. Is there any questions?
Hi, really interesting. I just wonder about, did you try anything to make /nix work anyway, like symlinks or user namespaces or bind mounts, that kind of thing?
So I've tried a few things. So symlinks, I came into the thing of saying like the symlink, the Nix store isn't allowed to be a symlink, and tried to work around it, and I don't know if you can actually patch around it, but I didn't get that working. User namespaces, a lot of the machines we run on don't have a kernel that's new enough to give you user namespaces. But ultimately that might become a nice solution, but not yet. The other thing I looked at is a piece of software called Parrot, I think. So the way this works is I think it's kind of like you do an LD preload hack to intercept the syscalls. And I did kind of get that working, but some of the security enhanced Linux syscalls that are used aren't supported by it, and I started patching them in, but then I found myself in a bit of a mess that I didn't have time to actually learn what I needed to know to patch it properly. So that might be another solution, but I didn't find myself having enough time to actually investigate it properly.
Other questions? Yes?
Hi, thanks for the talk. Is this a solution that's being in production?
Sorry, can you move the microphone a bit closer?
Sorry, is this a solution that's heading to production, or is it already running?
So at the moment, it's still kind of being investigated, subject to my time. Like I can start thinking about pushing it into production, but this is my side project, so it's as much time as I can find before I submit my thesis. But it's being taken seriously as part of this HEP Software Foundation set of recommendations. So it may come out as being the recommendation from that.
More questions? We have time. You finished early.
It seemed like a lot of the talk was about reproducibility of builds, I guess. How interested are you in reproducibility of experiments based on, is that kind of something that foundation is interested in? Or I don't know if I phrased that very well.
By that you mean other experiments being able to reproduce the results?
Yes, exactly.
Yeah, so that's kind of a separate thing that I'm also involved in, of trying to preserve analyses and knowing exactly how we actually produce results. And this can also help for just giving you a better idea of what software you used and being able to build these environments up again, which can be quite tricky. But.
More questions? Nope. Then thank you very much again for your wonderful talk. Such a mess. Where did I put my stuff? Yeah. Alrighty, so on to our next speaker, which is Edith. And on her behalf, I'd like to ask you to not take pictures of her and tweet them in the world. And also, I'd like you to pay note that you should refer to her as she and her. So thank you very much for that. And apart from that, she's here today to talk to us about NixOps. It's the limitation that she has run into using it, and the ways that she has found to do things better. Right? Off we go.
I'm not quite going to talk about NixOps in terms of how I've worked around it, but for starters, what do I actually do? I run a small platform as a service company called Mutable. We put the cloud experience in places where you wouldn't otherwise get them, in what everyone's now calling edge cloud. But that means we have to manage a lot of systems in a lot of places across diverse infrastructure, and the cloud never sleeps. So we got to be able to patch stuff up while it's running. We can't really have non-atomic updates to things because that's an operational nightmare. So somewhere around 2 years ago, we switched everything over to NixOS. We use immutable infrastructure practices to build everything outside the compute, but we have a constantly evolving stack, so we have to manage those as well. We try to solve problems at the lowest layer it makes sense for, so we have to integrate custom patches to all kinds of software, kernel patches, kernel modules. We have to integrate our system like as closely or at least we have to integrate our own software as closely with everything else as third-party software that we pull in. Like, we use console and things like that. We use a heavily modified Docker currently. But that's not such a huge problem if we're on NixOS. We run on diverse underlying infrastructure. We run on EC2. We're moving our control plane to Google Compute currently, but most of our targets are bare metal provided by telcos and places like that. So, and we have a lot of like machines we're deploying to, so we can't have like something where we're doing some like significant amount of per machine work. So I was aiming to deploy our compute nodes, which run basically a Docker daemon, a bunch of magic of ours, and our own services because our system runs on itself. So NixOps was my first choice when, like, okay, I have to deploy a bunch of machines with Nix. But NixOps is neat if you're deploying like a couple dozen machines. It has its like slightly more pet than cattle approach to deployment, where individual machines are things you're aware of. It sets networking hostname for each machine, so each machine already has a unique configuration. It sets etc hosts to contain every other machine, so every time you add a single machine or remove one, you're touching every machine you already have. You can like do networking to extra hosts, is make force empty string, that works out. But really what I want to do is always deploy a one-size-fits-all image to every single machine of a certain type, and then mutate it after the fact. Because we have things like custom kernels. NixOps likes to deploy the pre-built AMIs that get built with every NixOS release, we have to reboot those right away if we deploy them. And there's no real automation for that. That could be done by like matching booted system to current system, etc., but it's not ideal. We also on our bare metal targets want ZFS support. There isn't much of that, but that was ostensibly patchable. Then there's support for things beyond role compute. So on AWS and Google Cloud, that's things like security groups, storage buckets. There's some support for those, but it's not very comprehensive. But the real kicker was not being able to use it in a distributed fashion easily. We have a variety of people deploying. We're working on automating, deploying our entire stack, but also just we can't have that state exist on a single machine. Everything about our system is designed to account for the failure of. So in addition to that, we want to target a lot of places, and NixOps has been slow to integrate targets. We are not super up for hacking on a Python code base. So what we ended up doing was handling the role compute resources with NixOps, with a couple workarounds for the issues we covered, a bunch of bash scripts around it to take care of things like adding a number of new machines to the cluster. And we ended up covering the we ended up running into the managing of non-compute infrastructure. We used Terraform for that in the past already. And Terraform is a tool for managing immutable infrastructure generally built from like pre-built images. So the normal approach when you use Terraform and like the entire HashiCorp stack is you pre-build AMIs running like Debian or whatever, and you apt-get and do horrible things and all that to make your thing work, and you bake that into an image and forget about all the horrible things involved in making it. And if you ever want to change the running machine, you throw it away and replace it with a new one. Which, sure, but in our case, we have customer containers running on those machines, and we do need to actually do hotfixes from time to time. Some of them are physical machines, so we can't just throw them away. But Terraform has a lot of good sides to it. It has great operator control. Ahead of like deploying a change, you can run Terraform plan, which will tell you, like, hey, we're recreating this resource because it changed in a way that we can't do at runtime. It has a good story for using it in a distributed fashion. You can tell it to back its state store with etcd or an S3 bucket, though that one's not super clean, but there are a variety of options that mean everyone can just run Terraform on their laptop and not clash with anyone else. It has rather pleasant integration with other tools, so I ended up using them together. Oops, that is the wrong screen. So that is not right. So Terraform looks like this. Basically, you have a resource abstraction, and you have outputs, which is all that matters to the next layer, really. So I just do some horrible things and poke inside its state files and get all of those bits out. And I use that to deploy everything that isn't that isn't like actual machines. I used this Nix expression from inside my NixOps config, and then everything works with that. It's a little manual, but it's fairly workable. But we still have the issue of like, when we're using NixOps, we're doing a Nix copy closure to every machine. There's a configuration that differs per machine by default. Maybe there's something I'm missing, but I haven't seen any like significant integration with like managing a binary cache. But ultimately, what NixOps boils down to is kind of a fancy way of doing NixOS rebuild switch -- target host. And that's all we're really using it for at this point. So what I'd like to do and what I'm building is, we have excellent support for building disk images in Nix packages, well, in NixOS. So I build a single disk image per node type, and use that to boot fresh nodes when I'm like powering up new machines, or just like anytime I'm running a machine with a clean disk. So that gets turned into AMIs for EC2, Google Compute, like machine images, and for bare metal a netboot image that we boot over. Do not necessarily boot over PXE, but the netboot builder builds your entire everything into the init ramifs, so that's quite convenient. Once we have those machines up, we want to be able to change them without shutting them down. So every system image we build gets pushed to a binary cache, and then we just connect to the machines and tell them to run that. So for that, we in theory have to interface with a bunch of Nix bits. There wasn't a convenient Google Cloud Storage C++ SDK. There's a deprecated one and one that doesn't have the right APIs. That's Google's thing, I guess. So I decided to, most of our stack is Go, and I'd have to bind Go to the C++ stuff if I wanted to really integrate it closely with our tools. That was not something I was excited about. So I ended up implementing most of the Nix store protocol and building myself something that roughly re-implements Nix push, but you can easily back it with arbitrary stores without having to write C++. And something that pushes images, builds an image using the make disk image stuff, takes care of the per provider specific things. So now we have binary caches, and like images to boot machines from. I actually didn't. Sorry. This is lack of preparation. So I have this little thingy called nib, which takes like roughly anything you can execute commands on, and like will take care of, if you give it an XStore path for a system, of invoking that right. It's a ton of code because Go is terrible, but it's pretty easy to use. I have a little. It's roughly equivalent to a programmatic NixOS rebuild switch -- closure -- target host. So the binary like exposes the built-in support for using Go's SSH, doing it on a local machine, of course, and it also supports NixOS in an Illumos zone because Visanto and I at some point played around with that. Our stack on top of all this is a bunch of Go services running in Docker. Those get stuffed into a Docker container with this little thing called Nix2Docker. Mostly built because the Docker tools in Nix packages are very, very flexible, but aren't very fast. This just basically sticks a tarball, like takes a closure, sticks it in a Docker image tarball, does the minimal work necessary for that. Our service derivations are built with something called GoX, which I would very much appreciate the Nix and Nix stuff for, because we use import from derivation to do dependency discovery and build every Go package as an individual Nix derivation, which I'm not sure if it's a waste of time yet, but it's been working for a good 2 years now. So I think that it's all right. And sort of my future plans are like to like release that and make it into a polished thing. And for deploying our clusters, we're like working on more stuff that like has more awareness of cluster state, is aware of the subsystems it's deploying. Like we currently deploy Raft clusters like etcd and console with NixOps, and there's sort of the automatic joining stuff to build a cluster, like a logical cluster out of that at the layer of that software. That doesn't work out quite as well as having like your deployment software be aware of what it is deploying and what its state is. In general, we want like a more programmatic approach to it. We specifically want it to work in a distributed fashion, so there's no state that's on any single machine. And at some level, we need a stateful approach because we can't reboot running stuff freely. So I'm sort of working on a plan where I look at booted system versus current system, figure out whether I can upgrade the system on a given machine without like losing the ability to load kernel modules. And I'm still working on like a plan for doing CI for all this, but I'm hoping that's easy enough. And sort of our long-term plans are probably sort of changing how we use NixOS, because systemd has been giving us a lot of problems in container context. So I've been playing with building something on top of the S6 stack, which is an approach to service supervision that is a little more Unixy, and I hope will be very nice with Nix. But yeah, I think that was most of what I wanted to talk about. I'd have had more demos, but my laptop SATA cable failed, so yeah, questions time, I guess.
Alrighty.
At the end, you have mentioned that you're trying to move NixOS to a different process supervision mechanism. Is it right? Or like do experimenter in this area?
Yeah, I'm experimenting with that because like systemd's job scheduling system is like very surprising at times and duplicates a lot of like what we do on the NixOS modules end of things.
What is the name of the other one you're trying to use?
So S6 is it is the Scarnet Service Supervision Suite. It's one of the many like DJBware things that like solve this in a similar way. It's very worth reading about, and I recommend digging in. I can't really give like a full overview of it.
More questions? Nope. Then thank you again very much for your talk, Edith. Thank you. So next up, again, 30 minutes of